All right. So some of you guys already know that we had a test on Tuesday, and some of you are probably happy with your results, or not your results, how you did, and some of you are probably worried about how you did. I should have these results done a lot quicker than my last test. So this should be done soon so you can know what you got on that test. But if you feel like you didn't do too well, or if you feel like you want to get a couple more extra points, I'm going to provide these opportunities for you right here. If you want to earn some extra points towards this past test, I'm going to ask you guys to sign up on Khan Academy and on Calc. So I'm going to put those links into the chat right now. So the first one up is for Khan Academy. If you want to do this later, you can. The links will be in on Canvas as they are right now. There's a link for Khan Academy. Please make sure that you sign up using your school email and edit your profile so that it has your first name and your last name, so that when I go to give you credit, I'm able to see who you are, so I can give you those points. Khan Academy is a site that's going to have a bunch of videos and a bunch of practice problems that follow along those videos. I'm not going to ask you to watch those videos. I am going to assign them, but watching them, if you feel uncomfortable with the topic or you need a little bit more review, his videos are actually really good and they're pretty decent at explaining it. And I'm also going to be giving extra points for how much you watch, and also extra points for the extra practice problems that they have on their site. Okay, so that's one way that you can get those extra points, is just sign up, create an account, and then I'm gonna make an assignment later at the end of today once everybody's signed in, and I'll assign the assignment. So I can't assign it right now until until students join in. So once a couple students have joined in there, I will make the assignment for you to do that will go towards your test that you just took on Tuesday, and we'll keep using this along the way to help us review for our AP exam. Okay. The other site is called Calc. It's the same kind of idea. It has videos as well, but it's a different person, and then they also have a different set of practice problems. This one, I'm not going to assign anything just yet, but I will give you points just for signing in for it. We are paying for this one. Calc is one that's a premium service that we're paying for, so I hope that you guys all sign up and use it. We only have a limited amount of seats, so it's limited to our class, both period 3 and period 4. So just make sure that you do sign up so you don't lose. It should be fine. I think I told them the right amount of students, so it should work out. But yeah, here's the Calc link. Same thing. Sign up with your school email and make sure that God, that link is ugly. Make sure that you. Sorry, I got distracted. Make sure that you have your first name and your last name present on there, so I can see who you are. Okay. All right, that's that. And yeah. So get those done. Get that done at some point. Like I said, at the end of today, I'm going to assign your first assignment on Khan Academy. It's basically everything that we learned in Unit 5. So if you feel comfortable with it, you don't have to watch the videos. But if you feel like you didn't do too well, I suggest you watch the videos and try their practice problems. And I will add those points, those bonus points, onto your Unit 5 test score. So let's say you get like a 71%, and that's with the curve, let's say, and you're like not happy with the curve that you got a 71%. If you complete the Khan Academy with the quizzes that are on there, I am considering boosting up your grade up from a C- to a C+. I'm not going to go a full 10%, but I will go more than 5%. So it's a good amount. It's a good amount of things, and all you have to do is just watch the videos and try your best on the answers on there. Okay, so keep that in mind. Calc, just make sure you sign up on there. I'm going to put some assignments up in the future. You could, if you want to start it before the other, it's all open, by the way, for both Khan Academy and for Calc. If you don't want to wait for me to put the assignments on there and you just want to jump into it, you can. There's no harm, no foul. And then once I assign it, it'll show me that you already have it done, and you'll still get the credit. Okay, so it's just another resource for you to use. We also got, I heard that we got some AP Calc test review books from Princeton. Those Princeton review, those AP Princeton review book textbooks. AP Princeton, I can't spell Princeton, review books for Calc. I believe we got the 2021 version, I think. You guys might have seen this in the stores. I think we got this. I'm not sure. I got an email saying that we have some on campus. I'll double check with them. If we do have them. Oh, you were able to pick it up last week? Where do I go get them, and what time was going to go today? Oh, Media Center from 12 to 3. Awesome. Did they send you an email on this? Like, did they tell you? That was my job. I failed my job on telling you guys this. Yes, during spring break. Can I get those? Okay, so this is for you. These were ordered for you as a class. So please stop by. It looks like all you have to do is go to the Media Center from 12 to 3. Tell them that you're looking to pick up an AP. Is it this book? Those of you picked it up, Brian? Brian, yeah, Brian, you said you picked it up. Was it this book exactly? Or was something like it? Yes? And all you have to do is just tell them that you're there to pick up your AP Calc review book, I'm assuming? Yep, okay. So yeah, if you guys haven't done so already, please go do that. That's my bad. I should have told you guys this, but why didn't I tell you this? Either way, I slipped up on that one, so you guys can go and pick that up. I haven't gotten my own copy yet, so I don't know what it looks like on the inside. So it's a good book to have. A lot of these AP review prep books have good practice problems for you to do. They're a little bit more difficult and a little bit more tough, but that's the idea. It's a little bit more difficult than the AP exam, just so you can get used to it. Get used to techniques for solving these more difficult problems that we haven't actually got to touch yet. So just keep that in mind. Okay. All right. That's that. So that's all the review stuff, review books, all that in there. And let's go ahead and let's jump into today's notes. Yeah. If you want to title it, we're in Unit 6 now. Right. One more unit to go is going to be Unit 7. My units don't line up as well as the AP College Board units. But that's just because I tend to cut and snip things here and there and move them around, just because I don't like how some of the units have like a ridiculous amount of work. So we still cover the same amount of stuff. I just break it up so the tests won't be as ridiculous when we do our unit tests. Anyways, I digress. Let's actually get into today's notes. Unit 6, or my Unit 6, is going to be more integration, right? More integrals that we're going to be working with. But is a little bit different from the integrals that we've been working with. So just a quick refresher, right? You guys just took a test on this. Like, let's say here, if I had the integral from 1 to 3, right, of 3x squared dx, right? And I asked you guys to evaluate this. This is a pretty easy problem to do, right? You guys have hopefully gotten used to this. Right, you guys will see something like this, and I'm just asking for what's the antiderivative of 3x squared, right? What's the antiderivative of 3x squared? Most of you guys already know that the antiderivative of 3x squared is x cubed, right? The antiderivative of 3x squared is x cubed. Why? Well, if I take the derivative of x cubed, I end up back at 3x squared, right? And then all you have to do now is evaluate it from 1 to 3, and we just plug in those numbers, okay? And that was pretty much the gist of it. And we call these I didn't actually give you the name of this, but these are called definite integrals. Definite meaning that you actually evaluate them at specific values, right? So when you do this here, you don't really care about this function. You actually use that function to get your final answer, which is to plug in the 3 cubed minus the 1 cubed, right? There we go. So that's all well and good. Right, that's all well and good, because once you get your answer, you're pretty much done there. This is 27 minus 1, which is 26, and then you're done. That answer tells you what the area is underneath this curve, right? And you're done with that. It's good to go in your set. With indefinite integrals, though, it's a little bit trickier, right? It's a little bit trickier. Since we're not evaluating at any particular numbers, we're getting an actual function that is supposed to be the antiderivative of that function that you're beginning with. You're like, what? So for example, right, if I told you and I asked you to find the integral of 3x squared dx, right, you'd still probably tell me that that answer is going to be x cubed, which you will be partially right. You'll be partially right. you're not completely right. And you'll say, knock me, how's that partially right when clearly up here you were done with your antiderivative with x cubed? And I say, yeah, I agree with you. If you're evaluating your integrals, you don't need anything else. That's pretty much done. You plug in your numbers and you evaluate it. If you're not plugging in any numbers, right, for this guy right here, if you don't have any values for the integrals to plug in, no a, no b, right, you don't have anything there, this changes your problem quite a bit, right? This changes your problem quite a bit. This is called an indefinite integral. We don't have any particular values for our a and our b. And what the problem is this. Let me ask you this. Can you guys tell me, right, find the derivative of these problems right here? Find the derivative of this. And I'll give you an example. Let's say I ask you to find the derivative of x cubed, right? Find the derivative of x cubed plus 1. Find the derivative of x cubed plus 2. Find the derivative of x cubed plus 3. Find the derivative of x cubed plus 4. What do you think the derivative is for each of these functions I've written down? X cubed plus 5. What is the derivative of all these? Can somebody tell me? Anyone have any ideas? Any clues? They're all the same. That's right, Monica. They are all the same. If I take the derivative with respect to x for these all individual lines right here, right? This one would be 3x squared. Well, this one would also be 3x squared. This one would also be 3x squared. This one's also going to be 3x squared. This one's also going to be 3x squared. This one's also going to be 3x squared. And you can do this infinitely. Oh, Ava also said, yes, they are all the same. That is right. Thank you. Thank you. Now, if that's the case, and you could do this infinitely, you could also do this for negative numbers as well. And you could do this for infinitely many positive numbers as well. My question comes back to stand here then. If I do the integral of 3x squared, I know I'm supposed to get x cubed, but how do I know which one of these I get? How do I know which one of these I get? These are, if you look at them, they're all just constants, aren't they? They're all just constant numbers, aren't they? Because if you take the derivative of 1, it's 0. If you take the derivative of 2, it's 0. If you take the derivative of any constant, it's equal to 0, isn't it? So that's basically, if you consider it, it's basically like a family of functions, isn't it? It's a family of functions. We have like a plus 1, plus 2. We could also have plus 1.5, plus 2.2, plus 3.3. There's infinitely many there. How the heck am I going to have it so I can show that it incorporates all of those families of those family of functions, right? So one trick that we do, right? And you don't have to write this part down. I just want to show you here. There's one trick that we do to incorporate all possibilities, right? If I have here x cubed, right? Oops, yeah, x cubed, and then I have, aside from that, let's do x cubed plus 1, right? And then the next one is x cubed plus 2, right? And the next one is going to be x cubed plus 3. And you guys get the idea where I'm going with this, right? You can kind of see it. This family of graphs, they all have the same slopes for the derivatives, right? If you take the derivative right here, it'll be the same as the derivative right here at 1, right here at 1, and right here at 1. And you can kind of see it. It's going to go on, and you can do this infinitely many times. But you know, being mathematicians, we're pretty lazy. I don't want to sit down and write down infinitely many numbers because, well, first of all, it's going to be impossible to write down all of them, and also I'm very lazy. So one thing that we do is we let that number, that constant, be a constant c. That way, that constant c is a number that we know is a constant. We just don't know what it is. And we just call it c, and we let c be any possible constant you could think of. See? And so that way, if I were to move this c around, it covers all my bases, but the antiderivative is still the same. See that? So if I take the derivative of that, no matter what the c is going to cancel out. So that's our trick that we do to incorporate this. So when you do integrals that are indefinite and you write this down as your antiderivative, you're only going to get partial credit. In order to ensure that you've covered all your bases, you're going to have to tack on a plus c. And you'll probably have seen memes about this. Well, I don't know how many of you look at math memes, but if you're a nerd like me, a lot of calculus memes Not a lot, but you'll see them in there now. You probably, once you spot them, you can't unsee it. But a lot of them will tell you to make sure you don't forget this plus c if you're doing an indefinite integral. If there's no numbers for your a and your b, and you do the antiderivative still goes true, still holds true, it still goes through, right? If I go and say, hey, what's the antiderivative of x dx, right? That's going to be equal to x squared over 2, but don't forget the plus c. That's all it is. Don't forget the plus c. So if I have something like this, what's the antiderivative of 2x, right, dx? Why, that's going to be equal to x squared plus c. And you just need to not forget that plus c. That plus c is the one that comes into all of your antiderivatives when you have a indefinite integral. When you have no values for your a and your b, that plus c is there. I'm going to create a secondary video that has to deal with slope fields, which go more into detail as to why that plus c is there and how that works. But that's going to be for a separate time. I would talk about it today. I have a worksheet for it to do it with notes, but like I said, we only have like a month and a half to go, and I'm gonna have to start making extra videos for you guys to watch on your own if you're interested in that stuff. And I'm gonna say right now, you should be interested in that stuff because you will be tested on that. I know it sounds unfair. It's like me throwing a lot of stuff at you, but we gotta crunch time this stuff. I feel a little bit bad that we're rushing through it, but we got to. So, all right, any questions so far right now with the whole indefinite integrals? Hopefully it wasn't too bad. Hopefully you're okay with it. Like if I have, for example, here the integral of, let's say, x to the 4th dx, right? You guys are catching on to this, right? Hopefully you see it. The antiderivative of x to the 4th would be x to the 5th divided by 5, right? Plus c. And again, you can always double check this, right? Double check this. Take the derivative of x to the 5th over 5 plus c with respect to x, d dx, right? And see if you end up back at x to the 4th. And you should, right? If you take the derivative of x to the 5th, you end up with 5x to the 4th, all divided by 5. The 5's will cancel out, so you're left with just x to the 4th. The derivative of a constant, it doesn't matter what that constant is always going to be 0. So when you take the derivative of this does become x to the 4th, which looks like it matches up here. And that's all you have to really do. So now when we start doing these integrals, all I'm pretty much asking from you is don't forget the plus c, right? If you don't see any numbers here, don't forget the plus c. If you see numbers here, you don't need a plus c. You just plug it in and you evaluate it. If you don't see any numbers there, put the plus c at the end of it. I'm going to keep saying this over and over again. If you're dealing with these integrals and you have no numbers here and here, don't forget the plus c. Also, you'll note that if you do these integrals and you don't have any numbers here, you're no longer able to use your calculator. The TI calculator is great for evaluating integrals using like little techniques, and that's why it's a best like estimate tool. Sometimes it doesn't give you the exact values every single time, but just a heads up, this, if I could turn on my calculator, this right here, function option number 9, you see the integrals there, it requires you to plug in a number for a and your b. If you don't do it, it kind of does some wonky stuff, and it just kind of like doesn't know what to do. You get like some weird answers is what I'm saying. So just make sure you're careful with that, okay? All right. Now, with that being said, I'm going to give you a couple integration formulas, right? Some of them you already know. I hope you already know them. Like, I don't know if you realize this, when you do these power rules, right? You hopefully have started to see a pattern. If I ask you to do the integral of x cubed dx, I'm hoping that you see that most of you guys should know this, right? It's going to be x to the 4th over 4, right? All I'm asking now is that you remember to put the plus c with it. How do I know that it's x to the 4th plus 4? These powers kind of go up by 1 because when I take the derivative, right? When I take the derivative of this, the power goes down by 1, right? This becomes x to the 3rd, but the power comes down in front. So that 4 would come down here. Now, what's different about this one is we have to put it over a fraction so that way this 4, when it comes down, when I take the derivative, will cancel out, right? Will cancel out, and we're left with just x to the 3rd. This actually is a formula. This is actually a rule that we follow here. And this right here, you ready to get started on this? I'm gonna give you a list of pretty much all these integral formulas here. So let's write these down. Integration formulas. You could also Google this. They'll have them all there. Usually with the letter U, though, and we're going to talk about why they use the letter U, but we'll deal with that later. For right now, we're going to do these basic, maybe if you look that up, basic integration formulas. So we have here, the first one up is called the power formula. Or the power rule, if you want to just call it the power rule. The power formula is this one right here. If I have the integral of x to the n dx, right, n being some constant that does not equal to -1, any number except -1, and we'll talk about why in a second here, but check this out. Any constant besides -1, the antiderivative of that is always going to be x to the n plus 1 divided by n plus 1. Don't forget, though, of course, the plus c. The heck, not what kind of c is that? Don't forget the plus c. Why can't n equal to -1 for the power rule? Can anybody tell me? What happens if is that m equals to -1? Whoops. This is n plus 1. This is n not equaling to 1 for this power rule. Is that better? My handwriting got a little messy there. Yeah, n plus 1. But now here's my question. Why can't n equal to -1? What happens to the power rule if I was trying to find the integral, right? What happens to the power rule if I was trying to find the integral of x to the -1 power using the power rule? What would happen? What would happen if n was equal to -1 and I tried to use the power rule? It cancels out the power. And you know that that's not going to be the case, right? If I did use the power rule, if you try the power rule or the power formula, I'm going to just write power rule, right? If you use the power rule, this is what would happen. You'll end up with x to the -1 plus 1, which is 0 over 0 plus c. We know that, well, first of all, this is not happening, right? We can't divide something by 0. Also, we also know that x to the 0 is just 1. And we know as a class, if I take the derivative of 1, you sure as heck aren't going to end up back at x equals -1. You'd end up back at 0. So that actually is not the antiderivative of x to the power of -1, right? Does anyone actually know what the function is for a derivative that would give us x to the -1? And it might help to actually see it. Maybe if I rewrote it, instead of x to the -1 and I wrote it as x to the 1 over x, I'm sorry, the integral of 1 over x. Does anybody know what's the function that when we take a derivative of it will give me 1 over x? It's one of our basic derivatives that we do need to know, by the way. This actually does match out with something. The derivative of what with respect to x would give me 1 over x. There is a function that does this. It's one of our basic functions. Or not basic functions, I should say. It's one of the functions we should know. No. Anybody know? Anyone have any ideas? Any clues? What function? What function? No? ln of x, Brian, that's it. If you take the derivative of ln of x, you end up with 1 over x. Therefore, the antiderivative of 1 over x is going to be equal to ln of x. That's it. Don't forget the plus c, though. So when you have the power rule, that works really well and dandy, but it doesn't work very well when your power is equal to -1. When your power is equal to -1, the antiderivative of that is going to be ln of x plus c. ln of x plus c. How you guys? You guys doing okay? Right? I know these formulas are a little bit weird, but they're not too bad. They're not too bad, right? We just got to remember, like, okay, I'm thinking backwards now. I'm thinking what, when I take the derivative of it, would give me back to this power or this thing that I have right here, right? We also have the property that allows us to add and subtract fractions with integrals. This is one of the integral properties. Hopefully you guys remember it. If I have here the integral of f of x plus or minus g of x dx, right? It's the same thing as me doing the integral of f of x separated from the integral of g of x. Why is that such a big deal? Why is that so important? That allows us to do problems like this. This, by the way, is the an integral property. The addition, subtraction, integral property is, I believe, what they call it. I could just be making that up. But let me show you an example here. If I have here the integral, right, of 3x squared plus the square root of x plus 1 over x dx. This looks complicated, this looks annoying, this looks harsh to deal with, but thanks to our property of being able to add and subtract our functions together and split them up into different integrals, I can do these all individually. So I can do this as the integral of 3x squared dx plus the integral of, instead of the square root of x, I'm going to write that as x to the 1/2 power dx, plus instead of writing this as one, I'll just leave that as I'm going to write that as dx over x. It's the same thing as 1 over x, right? You know what? That might be confusing to you guys, so I'm going to write that as 1 over x dx. Which, by the way, is not anything different than dx over x, by the way. Some books actually prefer writing it this way, and they'll, you get the same integral. Anyways, it doesn't matter. Just to get you used to seeing it. But check this out. We do each integral by itself. So this one right here, 3x squared, using the power rule, right? I know that this is going to be, technically I'm supposed to show the work here. It's supposed to be 3 times x cubed over 3, right? Because that's the power rule. We plus 1 that and we divide by it. But what happens with the 3's here? The 3's should cancel out. So the integral of 3x squared is going to be just x cubed. And double check it. The derivative of x cubed is going to be 3x squared. So it does work. So that's right there. Don't forget the plus c. Then I do this one over here. X to the 1/2. X to the 1/2. I want to show the work over here. What's 1/2 plus 1? 1/2 plus 1 is 1.5, or in other words, 3 halves. 3 halves. But I have to make sure I divide by 3 over 2. This gets really messy if you leave it like this. I don't like leaving my answers like this, but it's technically correct. But if you want to make it look nice, the fraction that's in the bottom just gets flipped and written in front. This is the same thing as 2 over 3 times x to the 3 over 2. So that power is basically what you're dividing by, right? Even you use that power rule, just to give you a heads up there. This, of course, don't forget the plus c. Now, this is a different c, isn't it? It's the different, so I'm going to label it c sub 1 just to say, that's another c. It might be the same as the first c. It might not be the same as the first c. Plus the last one, 1 over x dx is the same thing as, well, the antiderivative of 1 over x we know is going to be ln of x, right? Thanks to the, it's not the power rule. I don't know if that actually has a name, but it's right there. And of course, don't forget the plus c as well. And again, this c is a different c from the other c's. And you'll say, knocking, that's a lot of c's there. And I agree with you. You technically don't need all these c's because I'm adding a constant plus another constant plus another constant. Does anybody know what happens when you add 3 constants together? What do you end up with? Any ideas? What happens when you add up 3 constants? What do you get? Any clues? If I add a constant plus another constant plus another constant, I get 3 times the constant if they're the same constant, David. That's true. Or in other words, just another constant, isn't it? A constant plus a constant is still a constant, isn't it? So when you do these types of integral problems and you have multiple plus c's, you can just put down 1 plus c at the end, and that's perfectly acceptable. And that would be your answer. That would be your answer right there. X cubed plus 2/3 x to the 3 halves plus ln of x plus c. That plus c at the end is the constant that covers all your indefinite integrals. It covers all of your indefinite integrals, and it's kind of neat. I like it a lot. It's like oh, that's it. I don't have to write it down multiple times, and no, you don't. Write it down once, and you're good to go. Any questions so far on any of these antiderivatives I've done? They look, there's a they're kind of funky. They're kind of weird, but they are a little a little strange, but they work. Hopefully, they're okay with you. All right. Next property I want to show you guys is the coefficient property. Coefficient property is one of the integral properties we learned in your 5.3 homework. It basically says if you have the integral of a coefficient times your function, right, dx, it's the same thing as the integral of that function by itself, and you just multiply by the constant after. So, for example, if I had something like this, what's the integral of 3 over x dx? And I kid you not, this is something that always trips up students sometimes because they see these fractions and they're like, I know that 1 over x is going to be ln of x, but 3 over x messes me up. So what you can do is take out that 3. So what I'm saying is rewrite the fraction as 3 times 1 over x dx. And that's perfectly fine, right? If I multiply that out, it'll still be 3 over x. So you can pull out that 3 from the numerator, write it like this. Why? So now I can rewrite this as 3 times the integral of 1 over x dx. And when you do that, this becomes 3 times, and you take a look here, this whole part is going to be ln of x plus c. Now this sounds kind of funky, but you can actually just finish this off and write this as 3 times ln of x plus 3 times c. And like we said earlier, 3 times c, 3 times a constant, it's still a constant. You don't need to worry about the numbers in front of it because, like I said, it's just a placeholder. We're just trying to figure out what that constant is. Okay? And that constant is just c in this case. So this is how we're applying those properties now pretty much when we do these integrals. And all we have to do now is make sure that we include these plus c values when we deal with it. Okay? The power rule is, the power formula is one of the more basic ones, right? And then we also have the one that catches it just in case our power is -1. I'm sorry for scrolling around too much. Give you guys a second to copy that down. Give me 1 second as well. All right. Sorry about that. Okay. With that being said, I'm going to give you a couple more formulas that you do need to know for antiderivatives. It'll help for you to have these memorized. Make some flashcards. I will be quizzing you randomly on these, not only the antiderivatives, but also the derivatives as well, just to keep you on your toes. You need to know them back and forth, and it just helps. It's not something that I'm trying to do just because I'm mean. It's just something that helps you since you're being timed when you take this AP test. So here's the next one. Trig formulas that you need to know. Trig formulas that you need to know. First one up. The integral of cosine x dx is going to be equal to sine x plus c. Right? And that's because, hopefully you remember this, the derivative of sine is cosine. Right? So the antiderivative of cosine is sine. Right? That's one you need to know. Another one you need to know is the integral of sine. This one's tricky. Anyone know what the integral of sine is? What's the antiderivative of sine? Negative cosine. I can't trick you. Can't trick you. It's negative cosine x plus c. Why is it negative cosine? Well, the derivative of cosine is negative sine. If I'm taking the antiderivative of a positive sine, that means that this should have been a negative cosine then, so I can get that. So that's that one. That's another one that you need to know. The next one that you need to know is this one right here. What is the integral of secant squared x dx? All right, and that's going to be, of course, tangent x plus c. So these are the three basic ones you need to know, right, for sine, cosine, and tangent. But you have hopefully already memorized these derivatives here, and you realize, like, oh, the antiderivatives of these specific ones are going to equal to this. On your review, I was very mad at myself when I looked at your review. One of them had the integral of tangent, and that was just me having a brain fart moment. I thought, like, you know, the integral of tangent is an easy one to do. It's not an easy one to do. That is not something that should have been on there. And I think the reason why I put it on there is because I forgot to put down the directions saying you can use your calculator to calculate it. If you ever see an integral and you have numbers here and here, and it doesn't specify to do it by hand, you can just plug it into the calculator if it's something that's really complex. If it doesn't have any numbers there, then we're going to have to learn these techniques I'm going to teach you today. But for earlier in the review in chapter 5, I feel bad. I should have told you guys you were allowed to use your calculator because you're doing definite integrals. And with definite integrals, right, we already saw that you can just plug in the numbers into the calculator. And that's my bad for not saying that. Anyways, with that being said, let's go over the last three basic ones, right? Let's go over the last three basic ones. The next one up is going to be the integral of I can never write this right, cosecant x cotangent x dx, and that's going to be equal to negative cosecant x plus c. Next one up is the integral. Hopefully you guys draw better integrals than I do. My integrals have been terrible lately. The next integral is going to be the integral of secant x tangent x dx, and that's going to be equal to secant x plus c. And the last one is the integral of cosecant squared x dx, and that's going to be equal to negative cotangent x plus c. So these are ones that you should kind of get yourself to know, but if you already know the derivatives of all 6 trig functions, you kind of know the antiderivative of them as well. Okay, so that's that one for the trig formulas. The next one up is exponential formulas. No, that's not how you spell exponential. Exponential formulas. That's not how you spell formula. Knock me. Get it together. Exponential formulas. All right. First one up is the easiest one. Do you guys remember this one? What's the antiderivative of e to the x plus c? Wait, e to the x dx. What is the antiderivative of e to the x dx? Well, that's asking you what's the derivative going to give you e to the x, and everybody's already typing into the chat. You guys already remember this one. It's e to the x, but don't forget plus c. Don't forget plus c. It's very important. Plus c. Yeah, plus c. All right, let's keep going. That's not the only exponential form, is there? That's exponential with base e. That's the easy one. This is the more difficult one. This is the one that shows up randomly, and I always hate it when it showed up. What's the integral of a to the x dx? Meaning the base is anything else other than e. E is a constant, but e is a special constant. It's that antiderivative of a natural log, right? Not antiderivative of a natural log. What am I saying? It's the inverse of a natural log function. But if we just had a, the antiderivative of a to the x dx is actually going to be a to the x divided by ln of a plus c. And you'll probably go, knock me, what the heck? And that's just because back when we learned about derivatives, right, we learned about this derivative as well. A to the x, if you take the derivative of a to the x with respect to x, it's going to equal to a to the x times ln of a. That's where this is coming into. And the reason why we don't do that when we have e to the x, well, we actually do it. We just don't show it. It's actually equal to e to the x times ln of e. But do you guys know what ln of e is? Ln of e is just 1. That's why with e, it's a special case. It just goes away. With a, with any other number, it was base 2, base 3, base 5, base a billion, you need to not forget about that ln of a. So when I do the antiderivative of it, I need to have this ln of a down here so that it will cancel with that ln of a if I were to take the derivative of it. Okay? I know I'm throwing a lot at you right now, but this one doesn't show up as often, but it's one that helps a lot if it's one of those things like either you know it or you don't know it. It's one that I was never able to, I shouldn't say it that way. You might be able to derive it, but in order to derive it, you need to also know the derivative form of it. So yeah, just giving you that heads up. All right. Last but not least, when we were learning derivatives, we learned these special cases, right? We learned power rule, we learned trig derivatives, we got these exponential derivatives. There's one last one for special derivatives, and this one last one is going to be the inverse trig formulas. There's 6 inverse trig functions that we did derivatives for. For the antiderivatives, you're really only going to need 2 of them. There are 6 of them, but honestly, most of the time, they're going to be of this form, okay? And the first one up is going to be this one right here, the antiderivative, or I'm sorry, the integral of 1 over the square root of 1 minus x squared dx. The first one up is going to be the inverse sine of x is one that you need to know, plus c. The next one up that's usually common that shows up on this if they are going to do the inverse trig function excuse me, is going to be 1 over 1 plus x squared dx. And again, this one is going to look like the inverse of, I'm sorry, yeah, the inverse tangent, sorry, of x plus c. And this last one I'm going to show you is one that's a little rare, but it has shown up every now and then. 1 over x times the square root of x squared minus 1 dx. And this one is going to be secant, the inverse secant of x plus c. What gets really annoying is these inverse trig functions. Once you know them, it's not enough. Sometimes they mess with you. They'll I kid you not, they will mess with you on these ones. They'll give you like some other things that go in for x that makes it look different, but it kind of follows the same way. And I'll give you one example right now. If I was looking at the integral of 1 over, you ready for this? 1 plus 4x squared dx. This doesn't look like it's going to be the tangent function, but it actually is, because if you look at it closely, this is the same thing as 1 over 1 plus 2x squared. And that 2x is some stuff right here that's very similar to that stuff that's in there. So when I do the antiderivative of this, right, when I do the antiderivative of this, this is going to equal to the inverse tangent of some stuff plus c. Now, what's that stuff that's in there? What's that stuff that's in there? The stuff that's in there is not just x, but it's going to be 2x. And if that is the case, your answer is not done like this. Because if you do the derivative of this, you remember the thing that we learned, the more advanced technique when we started taking derivatives? If you have a function inside of another function, we have this thing called the chain rule. So that means that I need to make sure I divide by the derivative of 2x, and the derivative of 2x is going to be equal to 2. And that would be the answer. And this is what I mean, like they'll just do that small little tweak. It's a very small tweak. This little 4 right there, you got to admit, that's not a big deal. But it's a big enough deal to affect your antiderivatives. And we're going to talk more about this here. What are we going to do when we have to chain rule our antiderivatives, right? When we have to chain rule our antiderivatives, it's going to mess with us a little bit. Okay? Actually, let's take a look at some of those things now. Actually, what happens if I do problems and they do have chain rules in there? How would I get the antiderivatives of those things? What's something that's going to help me with that? And that's what leads into this next one right here. Are you guys okay with this so far? I'm gonna slow down a little bit. Are you guys all right? I need to check in with you guys. Have I lost anybody here with these formulas of these integrals? Are you doing okay? Are you doing all right? This is the time to speak up, by the way. Don't just hold back and you're like, I have no idea what's going on. I'm just not gonna say anything. Because if you don't, I'm just assuming that you're all absorbing it and you're all getting it and you're all just amazing. Which is, is possible, but you gotta let me know if you're struggling, okay? I'm just gonna keep going. No one's saying anything. All right. I'm all right. You're all right, Max? All right. Thanks for at least let me know that you're all right. I do appreciate that. All right. So those are some basic integral formulas. You think you am? You think you are too? I think I am too. That sounds right. All right. Oops. Yeah, that's good. Okay. I'm glad that you're at least letting me know that you think you're okay and you're feeling like you're all right with it. I do appreciate that. All right. So let's go to this one right here. Let's do a problem that involves the chain rule, right? Let's do a problem that involves the chain rule real quick. You ready? Let's look at one problem that has the chain rule. How would we attempt to take the antiderivative of that? So let's go the easy way that we know how to do it. Let's take a derivative of something that involves the chain rule, right? Let's say I ask you guys, what is the derivative with respect to x of e to the sine, geez, knock me, e to the sine of x, right? If I was taking the derivative of e to the sine of x, what would that be? What would that be? And hopefully you guys remember, right? We had to use the chain rule for this. Chain rule. which states I need to look for the inside function, and I need to find the outside function, and then take the derivative of each one. The inside function in this case is sine of x. The outside function is e to some stuff, right? The derivative of the inside function, derivative of sine, is cosine of x. The derivative of the outside is still e to some stuff. But that stuff, of course, is sine of x, right? Sine of x. So the derivative of e to the sine of x is going to be cosine of x times e to the sine of x. Now, this is what I mean. If I'm looking at a problem that looks like this looks horrific. I hope you, I don't hope you agree with me, but I think you'll agree with me. If I told you guys, hey guys, what's the integral of cosine of x times e to the sine of x dx? And if you were to look at this, you'll probably go, what the heck? How do you even start a problem like that? But you know that this is just the derivative of this, right? So this actually would actually be becoming e to the sine of x plus c. Now, that being said, if I didn't have this part right here to show me what the derivative is and what the original function was, I would not be able to do this problem. Not just by knowing it. I don't know the antiderivative of this off the top of my head. And that's because it's a function multiplying with another function that has a function inside of it. Right? That's just pretty much the idea there. It's just like, what the heck? What the heck? So there is a technique to help us with this. When you have functions that clearly have a function multiplying with another function, usually we or a function inside another function, we think of the chain rule, right? And when you do the derivative using the chain rule, it wasn't too bad. We had to identify the inside function, the outside function, take the derivatives and multiply them together. For integrals, when you think that there's a chain rule being used for the derivative, we don't call it the chain rule when we go backwards. And we call it something else. And this is what I'm going to tell you right now. That technique that they call it is called the U Substitution Method. Some books just call it the substitution method. Some books just call it the U method. Some books call it the U substitution method. They combine the two. And the idea is that you're allowed to switch out the variable inside with this letter U. And you'll say, why? And when you think about it, the chain rule has to deal with you multiplying the derivative of a function of the inside function with the derivative of the outside function. So let me show you what this is going to look like. So let's do an example problem here. So let's say I was asked to find the integral of 2x times the square root of x squared plus 1 dx. Give you guys a second to copy that down. Give you guys a second there. Excuse me for a second. Basically, what you're trying to look for when you're dealing with something like this is you try to see, first of all, are you able to see that this is more than one function? You can break up this function into pieces of functions. Does that make sense, is what I'm trying to say there? Most students will just look at a function and say, that's the function I have to deal with. The next skill you need to be able to do now is see that some functions are pieces of functions put together, right? Can you guys see that this has two functions multiplying with each other? One function being 2x, and the other function being the square root of x squared plus 1. And even that function right there, the square root of x squared plus 1, can be broken down into two separate functions. I know you're saying, what the heck is this guy talking about? Let's say this whole thing is the function you're dealing with, right? But this whole function has basically three functions that you're dealing with. One function being 2x, another function being x squared plus 1, and the third function being the square root of that function. This is a composite function right here. And if you can take a look at something like this and break it down into pieces of functions, it's going to make this a little bit easier to deal with. And if you aren't able to do that, you'll still be able to do this. It's just going to be a little bit more difficult. But basically, what U substitution is doing is you're looking for a function that looks like it's a derivative of one of the other functions. And some of you might have already spotted it. And some of you guys are still saying, what the heck are you talking about? And that's, sorry, I'm having vivid flashbacks of myself getting very angry at this. Just like, what is this guy talking about? Just do the integral. And you'll agree, right? I don't know what the antiderivative of this is because I don't have a property that deals with multiplying two things together. I do have properties if they were adding and subtracting, but not when they're multiplying together. When they are multiplying together, we have to use U substitution. And when U substitution comes into play, this is how it works, okay? You look for a function that looks like it's a derivative of another function. And I'm saying this right here. Can you guys look at 2x? Would you guys agree that 2x looks like it's the derivative of x squared plus 1? Does it look like it, right? It doesn't have to be perfect, but it looks like a somewhat close match. That's all it does. And Monica's saying yes. And some of you guys hopefully will notice, well, if I take the derivative of x squared, I do end up with 2x. So that's what he's trying to say, I think, but he's just wasting a lot of time. So here's what the technique is. You ready? We go off on the side and we let U equal to the function that looks like it's the antiderivative of the other function. Let U equal to x squared plus 1. When I let U equal to x squared plus 1, right? When I let U equal to x squared plus 1, I'm hoping that you see this, I end up with, well, I can just replace this whole thing with U. But check this out. If I take the derivative of this with respect to x, or if I take the derivative of both sides, I end up with this thing called a differential equation, right? The derivative of U is going to be du, okay? And this is going to be equal to the derivative of x squared is going to be 2x, and this will be dx. This is something that I'm skipped over. This is something we should learn when we were learning slope fields. We call this a differential equation. This is a little bit different from the du dx deal, but if you want to connect it, some of you might see it. It's the same thing idea as this right here. Taking the derivative with respect to x would give me du dx is equal to 2x. I'm just writing it like this. It makes it easier to see. Anyways, if that's all mumbo jumbo to you, just come back over here. What I'm doing to go from this step to this step is I'm taking the derivative of both sides of the equation. I'm taking a derivative of u, and that's going to give me du. I'm taking the derivative of x squared, which is going to give me 2x. The derivative of 1 is 0, and the 2x, of course, gives me the dx as well. We'll talk more about that later. But for right now, check this out. You ready? You ready for this? X squared plus 1 is the same thing as u. So what I can do is replace x squared plus 1 with the letter u. So I can write this down like this. This is going to be the integral of the square root of u. Right? I replace the x squared plus 1 with u. The 2x dx right here, if you look at it closely, matches this 2x and matches this dx. So what I could technically do is write this down as 2x times dx. And I can take these 2x times dx and replace it with du. With du, right? I'm substituting out what they can equal to. When I substitute out what they can equal to, I can get these values right here. Now, check this out. My new integral here is going to be the integral of the square root of u du. And I think that's a little bit easier to deal with, right? I can just rewrite this as the integral of u to the 1/2 du. And I can go ahead and I can do this integral, can't I? The integral of u to the 1/2, I can just use the power rule that I learned earlier today, the power formula, right? This is going to be u to the 1/2 plus 1 is going to give me 3/2, right? Because that's the power rule. Let me write that off on the side. Power formula, just to show the work here, if I have here the integral of u to the 1/2, that's going to equal to u to the 1/2 plus 1 divided by 1/2 plus 1. So I need to also divide this by, well, actually, I'll write this off over here. This is 1/2 plus 1, which is going to be the same thing as u to the 3/2 divided by 3/2. But when I divide by 3/2, that's just the same thing as, if I flip it, it's the same thing as 2/3. Don't forget what, by the way, once I do this integral, I know it's a lot of work there, but always, 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 even if you're doing this power rule with a U substitution, you still can't forget that plus C. That plus C still comes into play. Now, I'm almost done. I'm almost done. It looks like you finished your integral, but you haven't. You haven't. You ready? You need to go back and substitute back out, what did we let u equal to begin with? And what was u equal to begin with? U was equal to x squared plus 1. So here's what my final answer is going to look like. You ready for this? You ready for this? This is going to equal to 2/3 times x squared plus 1 to the 3/2 plus c. And that's your answer. And that's your answer. That's how U substitution works. It's a technique that helps us to deal with the chain rule of a derivative, but going backwards. And if you don't believe me, something that you should do on the side right now on your own time, take the derivative of this. Take the derivative of this with respect to x. I guarantee you, you'll end up with this answer. If you take the derivative of this, I guarantee it, you'll end up back over there. And that's what the chain, that's what U substitution is for. It's a technique that helps us with a little bit more difficult integrals. Right? That's what it's helping out with. Hey, dog. In the middle of teaching class, right? Oh, okay. Just sneeze all over my water bottle and then leave. All right. But yeah, that's what U substitution is for. And don't worry if you don't have it in one try. We're gonna do We're gonna do this quite a few more times. Okay. So let's do one more problem, and then I'm gonna give you. Some of you guys prefer like an outline, so I'll give you an outline. All right. So let's go ahead and get this down here. Let's do another example here. So I'm going to have here the integral of x squared times the square root of 5 plus 2x cubed dx. Write that down for a second. I can't play right now, dog. I'm in the middle of teaching class. All right, there you go. All right. Give me a second. I'm going to close the door again. Hi.
Little class. You're going to hurt us together.
Yeah, she is. Hey. All right. Oh, dog. Okay. So, following the technique we did earlier, right? Following the technique we did earlier, let's take a look here. Does this right here does the x squared look like it's possibly a derivative of the other one? Does one of them look like the derivative of the other one? Does x squared look like it's a possible derivative of x cubed? And I'm hoping you guys will say yes, right? Because x cubed, when you take the derivative of it, you end up with x squared. But the number in front isn't going to match perfectly like what I have, right? And that's going to be okay. So here's what I'm going to do, right? This right here kind of looks like it, so I'm going to let that be the case. And it looks like it might be the derivative of that. So you just try it for this one. So I'm going to go off to the side. I'm going to let u equal to 5 plus 2x cubed. All right. Now, after you let u equal to something like that, you go ahead and take the derivative of both sides, right? So take the derivative of u, I'm going to end up with du. The derivative of 5 goes to 0. The derivative of 2x to the third is going to give me 6x squared dx. 6x squared dx. All right. Now, check this out. What I'm going to do right here is take a look at what I have so far. My 5 plus 2x cubed looks like I can replace this right here. And I can replace the 2x. Let's do that in orange. I can replace the x squared with this x squared, and I can replace this dx with this dx right here. What do I have that's an extra amount right here that's not going to help me out here? This extra thing that I have that I don't want to have is this 6. Do you see it? There's no 6 there, right? There's no 6 there, so I need to find a way to get rid of it. So what I'm going to do is divide both sides by 6, and that's okay, right? We can do this with our formula. I end up with du over 6 is equal to x squared dx, right? X squared dx. Now that I have x squared dx is equal to du over 6, I can replace this x squared dx with just du over 6, right? I can replace that. And by the way, everything's multiplying together, so you can move things around, right? So I can put these guys next to each other just to help me out. So what I'm essentially doing is this, right? I'm rewriting this as the square root of 5 plus 2x cubed times x squared times dx. I'm putting the x squared and the dx next to each other, so I can see that I'm replacing it with du over 6. That's what I'm doing here. Then once I do that, I can go ahead and replace the 5 plus 2x cubed with u. So I end up here with the integral of the square root of u times du over 6. Now, why is that a big deal? Why am I working so hard to get to here? Because now I end up here with the integral of u to the 1/2 times du over 6. And you'll say, that over 6 still makes me feel uncomfortable, Knock-Me. I don't like dealing with fractions, but fractions aren't that bad, especially if there's no variables involved with them. Du over 6, hopefully you guys agree, is the same thing as 1 over 6 times u to the 1/2 du, right? That's what the du over 6 is. It's the same thing as 1 over 6. Now that 1 over 6 is the same thing as a coefficient, right? Which means I can take that and write that in front as 1 over 6 times the integral of u to the 1/2 du. And I know that's a bunch of steps there. You can actually skip those steps, but I just wanted to show it to you. Once you go from up here all the way down to here, this right here is just the power rule again, isn't it? So when I do this integral, this is going to be 1/6 times, and I just have to do this antiderivative right here. This is going to be u to the 3 over 2 times 2 over 3. And I only know this because we did this earlier, right? Plus c. Plus c. Right? Plus c. Now we're almost done. We got to go back and replace our u with what we have it to be equal to, which is 5 plus 2x to the 3rd. You can distribute the fraction first if you want, but I'm just going to show you what this will look like. This is going to be 1 over 6 times 2 over 3. And inside here, the u function that we had was 5 plus 2x to the 3rd. 5 plus 2x to the 3rd. This, of course, is all being raised to the power of 3 over 2. And this all, of course, is a plus c. And this is it. This is our answer. And if you really want to clean it up, you can distribute this fraction right here of 1/6 multiplied by 2/3. This is going to give me 2 over 18, or in other words, 1 over 9 times 5 plus 2x to the 3rd raised to the power of 3 over 2 plus c. And that is my answer. I know it seems kind of funky and seems kind of weird, but U substitution is a very, very nice technique that helps us to deal with chain rules. I know it's just like when you look at something like this and you're just like, how the heck am I supposed to get the antiderivative of that? It's these steps right here. These steps right here. There's not a shortcut, but a different technique for finding out how to substitute in for this step right here. And I'm going to put that down right now, but I'm going to give you guys a second to copy this down. And if you're already done copying this down, I'm going to give you a second to copy this down. Excuse me. Here's what I want to give you guys to take from this. This is the steps for doing U substitution. It can be broken down into 6 steps. First one up, determine which factor is a form of the derivative of the other. That's what we did up here. We saw that x squared looks like it's a form of the derivative of 2x to the third. It's not perfect, right? This one doesn't have a 6 in front of it, but x squared is definitely a derivative of x cubed. Right? We deal with the coefficient. We deal with the number in front later. Step 2, let u equal to the factor that is not the derivative. Let u equal to the factor that is not the derivative. Okay. Step 3, find du from part 2 and isolate dx. This is the part that's a little bit different from what I was doing in my notes. I did not do this part. I did not isolate the dx. I like looking for the factors that match manually. It's just easier. It's just how I learned to do substitution. I would look for factors that match perfectly and then try to solve for it and then replace it with what it's equal to. The technique that's being written here is a little bit easier for some students to deal with substitution if you don't feel like you're strong with substitution. And that is to solve for dx. That's what it means to isolate dx, is to get dx by itself and then replace just the dx and see what you get. And I'll show you what that looks like. Next one up, substitute the u form and the differential form into the integral and simplify. So basically substitute in the dx and substitute in the u into the original equation, and this is what you would end up with. Once you get to here, you should be able to integrate this new integral. It gives you a form that's going to be a little bit easier to deal with. It's usually like a chain rule. I mean, it's usually the power rule or a simple trig function rule that you understand or you know how to do. Once you integrate, last one is to change the variables back to the original. So you can't leave it in u form. You have to plug in back here the original form in for u, and then that will be your answer. I know that's a lot. And things are getting a little bit more complicated. But that's just how it is. This is the second part of it, of calculus, and it's one of the more annoying parts, but once you get the hang of it, it's not too bad. You're just looking for different techniques for finding the integral, right? For different functions that you're going to be dealing with. But yeah, that's that one right there. Let's do one example using this technique. Yeah, let's do one example using this technique, and then we'll we'll call it a day. So let's take a look here. Are you guys able to copy all this down? Hopefully you were. I'm gonna go ahead and scroll off of this. If not, I'll put the recording up later today, and you could just pause where I was at and copy this down later. All right, let's take a look. Let's take a look here. Is it like this? Yeah, let's go with that. Okay, let's take a look at this one right here. So let's have here the integral of 2x plus 3 divided by the cube root of x squared plus 3x plus 6 dx. Now, if I didn't have this U substitution technique and I was trying to do it using the power rule, I would be screwed. Like, that's just literally, I do not know if there's any rules right there. We also didn't learn about any rules of dividing functions with another function, right? So for right now, the technique that we have that we're going to use is the U substitution method. Now, does one of these look like the derivative of the other? Does one of these factors look like a form of the derivative of the other? Does x squared look like it's the derivative of 2x, or does 2x look like it's the derivative of x squared? Monica's saying yes. She sees that one of them is definitely looking like the form of the derivative of the other. You guys see it? This is what I'm talking about here. Hold on a second. My OneNote is bugging. Give me 1 second. I don't know why my OneNote does this every now and then. Oh, it's whenever I copy and paste, and I have no idea why when I copy and paste it just decides to like, hey, you want to change your markers into highlighters? You can't anymore. So let's try that again. You guys see them? You guys see these functions? The two factors. Here's one factor. Here's the other factor. I'm hoping you see that 2x does look like a form of the derivative of x squared, right? Because the derivative of x squared is going to be about 2x. Now that I see that, I'm going to let u equal to the form that is not the derivative. That is not the derivative. And x squared plus 3x plus 6 is definitely the one that's not a derivative. Right? That's the one that's not a derivative. All right. Once I have that, find du from here, meaning take the derivative of both sides. So the derivative of u is du. Find the derivative of x squared is going to be 2x. The derivative of 3x is going to be plus 3. And this, of course, is all being multiplied by dx. This, of course, is all being multiplied by dx. Now, this is the other technique. Like I said, I usually just like to look for it, and I can kind of see it right here. The 2x plus 3 times dx is right there, and I usually just like to go from here and just substitute out and say, hey, that's equal to du. But some people, like I said, aren't comfortable with that. So some people will like this technique instead, which is to, in step 3, isolate the dx, meaning get the dx by itself. So I'm going to divide both sides by 2x plus 3, 2x plus 3. So I end up with this right here. Du over 2x plus 3 is equal to dx. And the reason why they prefer this is then once you do this, you can actually see what cancels out into the actual substitution here. So you ready? I'm going to write this out right here. Let u equaling to this, and I have dx equaling to this. So here's what I do now. Step 4, substitute everything out. So in here, I'm going to have here, this is 2x plus 3. I'm not subbing that out just yet. Over the cube root of u, right? Over the cube root of u, because I'm replacing x squared plus 3x plus 6 with u. And then I'm going to be replacing dx with du over 2x plus 3. I'm almost out of time, I just realized. But check this out right here. The 2x plus 3 cancel each other out. I'm left with this integral of 1 over the cube root of u du, which is the integral of u to the negative 1/3 du. And I'm going to leave that there because I'm out of time. But you guys can use the power rule now to take that antiderivative. I actually suggest that you guys attempt that problem. It's 10:37 now. Thanks for listening for this nonstop lecture. It's been a lot to cover and a lot to talk about. So hopefully you aren't too exhausted. But yeah, if you have any questions, stop by my office hours later today from 1 to 2. And if you could, please get started on those review things. Sign up on to Khan Academy and on to Calc Medic. All right. Other than that, have a good rest of your day, everybody. Have a good weekend. I won't see you until Monday. Stay out of trouble. Stay out of jail. Don't get pregnant, everybody. I'll see you later. So long. Farewell. Auf Wiedersehen. Bye, everybody. Whew.